So different papers introduce different architectures. Attention is all you need introduced an architecture of a very complex transformer that had multiple subblocks. Then a decoder-only transformer had its own architecture where we did not have any encoder and which turned out to be a large language model and then which turned out to be an application layer or basically a full-fledged application that can be exposed to an end user, which is known as ChatGPT or Geminis of the world. But what does learning look like? What does training look like? What the hell is training? Intuitively, training a large language model or training for a large language model is simply nothing but learning, right? What learning? So any large language model, or for that matter, any neural network has to learn a lot of things. What are those lot of things? They are problem specific things. Let's take a simple neural network. A simple neural network will be fed a lot of data points depending on the data that we're dealing with. If we are dealing with tabular data, which is organized in a CSV, we will feed each row one by one, one by one. Let's say we are doing a sequential training and we are not doing any sort of batch training. So we'll feed the rows one by one and ask the neural network to learn all of these data points to make sense of them. Making sense of them is, programming and reprogramming its weights and parameters. That is what the making sense of the data points means. Now, for a neural network that is dealing with images, instead of a CSV data point, we will feed them images. We'll feed them a lot of images, right? For example, let's say we want a neural network to classify the difference between cats and dogs. So we'll feed them, let's say, 10,000 images of cats and 10,000 images of dogs, right? So that they can understand how do I differentiate, what are the intrinsic patterns, what are deeper hierarchical relationship between cats and dogs, such that if given an unseen image, I can recognize whether it is a cat or a dog. To make a generic neural network, we can feed them all the images on the internet, right? Let's say if I want to build a neural network that can not only classify cats and dogs, but immense amount of objects, right? For example, let's say I have a data set which is known as ImageNet and Tiny ImageNet. They have over 200,000 classes or 20,000 classes. So if we feed them all of the data set that is there in the ImageNet, and if we ask the neural network to learn the representation of all of these classes, what do I mean by learn the representation? So statistically, neural network is going to represent each of the image in some higher dimension, right? That dimension is also known as latent representation. And it will learn that representation. It will not memorize the image. It will not genuinely memorize what are the edges in the image, what is the facial morphology of a cat, what is the facial morphology of a dog, does cat have whiskers, does dog have whiskers, does cat have a tail, does dog have a tail. It's not going to memorize that. It's going to represent each data point or basically each image in some higher dimension and learn that dimension. When we say learn that dimension, imagine a disc jockey playing some music, and the objective of the disc jockey is to get everyone in some harmony and elevate everyone's energy. So the disc jockey will tune up, tune down all of its nozzles or knobs, so in order to maximize the elevated energy of the whole crowd, right? So this is what learning is. So whenever a neural network is learning, what mathematically it's doing, mathematically it is adjusting all of its weights and biases in such a way that the loss is minimized. Now, what is loss is basically your objective function, your cost function. So you have to define a loss before you start training. For a neural network for that is classifying images in dogs, they might be following a binary cross entropy loss. For a neural network that is going to predict the house prices, given all of the information of different houses, let's say in New Delhi or in Hyderabad, it is going to have a mean squared error loss or root mean squared error loss, right? So we have different loss functions for different problems. Neural network follows cross entropy loss, right? So largely what a neural network is going to need mathematically to be able to train itself or to be able to undergo training of one objective function, a lot of data points. In the neural network, the data points are nothing but tokens. They are not images, they are not CSV files, right? They are tokens. So it's going to need a lot of tokens that on which it's going to be trained on. The token will have its own set of vocabulary, and each of the token itself is going to be known as a data point. Now, what the neural network has to learn, the objective of the neural network is to predict the next token, to assign a probability to each token in the potential vocabulary so that we can sample the next token from those probabilities. And let's say there are 50 tokens in the output head, right, of a neural network. Each of the 50 token will have a probability. Let's say P1, P2, P3, P4, P5, and P50. I will pick, the maximum probability for that particular token, right? So now, in order to generate the next token better, neural network has to undergo training. The first iteration of training, the neural network will generate random gibberish tokens, right? That because it has not been trained yet. But we would realize when it undergoes training, right? Let's say it undergoes training on the whole internet data, the tokens that it is going to generate are making sense. They follow a pattern, they follow an English like language, they're able to represent a language, and they are able to make sense in the with respect to the previous token context, right? So from gibberish to a perfect English like token, this happens because of training, right? Now what exactly is training mathematically? So once we have defined a cost function or an objective function, we know that a transformer, which is a neural network behind a large language model, has a lot of parameters. So if we try to revisit what were the parameters, all the token embeddings are parameters, because they are trainable. All the attention metrics like WK, which is the key matrix, WQ, which is the query matrix, WV, which is the value matrix, all of these are also trainable parameters. Then WO, which is the projection matrix, right? Along with that, we have the feed forward neural network. So all the weights and biases in the feed forward neural network. So let's say WFFN, biases FFN, right? So all of these are trainable parameters in case of a neural network. We are assuming that positional embeddings are also trainable. So let's take them also, right, as trainable parameters. Now we have to adjust them, right? We have to tune in the knobs. We have to, weigh them up and weigh them down, right? So how do we do that? Right? So in the first iteration, when we do the forward pass, which we discussed in the last video, we are going to produce a probability. That probability and the token is going to be random, right? And random in the sense it might not make sense. It might be English like characters. It might not be very complex mathematical symbols, but it might not make sense in the sentence. Let's say it might not do a great autocomplete suggestion. It might not do a great sentence continuation token, right? So it's going to be gibberish. What we'll do is we will backpropagate. The idea of training is to use an algorithm that can update all the weights and biases, of the whole model such that the objective function or the loss function, the cost function, all of them, all of the three names I use interchangeably are minimized, right? So imagine a U-shaped convex function. You are standing here where the loss is maximum, and you have to iterate and come down at the bottom where the loss is minimum, right? You have to, where the loss is minimum, those are the best parameters suited for your neural network, for your transformer, right? Or for your large language model, right? On top of the stack, on top of the abstraction sits large language model. People call large language model a neural network. If you come down and observe what kind of a neural network is, it is a transformer, right? So always remember the stack, right? So when we call a neural network when we call a transformer a neural network, we're just trying to abstract out information and talk to a noob, talk to a layman. When we want to be more precise, we call it a transformer. When we want to be even more precise, we call it a decoder only transformer that is generative in nature, right? So we can be as much precise as we want. So now what is going to happen in case of backpropagation or the training algorithm? The training algorithm is also the backpropagation algorithm, right? The backpropagation algorithm intrinsically uses something which is known as gradient descent, right? So no matter what you are training, no matter you are training a simple artificial neural network, or you are training a convolutional neural network, or you are training a linear regression model, or you are training a logistic regression model, or you are training a complex transformer, or you are training a recurrent neural network, all of these neural networks use the essence of gradient descent. They follow the same mental model. What does that mental model says? The mental model says take a partial derivative of the loss function or the cost function, right? So what do we mean when we want to say take the partial derivative? We just want to differentiate, right? We want to differentiate the loss function with respect to all the parameters. So when we take a partial derivative, let's talk simple. Let's say there are two parameters m and c, right? And the loss function is noted as L. I want to take the partial derivative of L with respect to m, right? In order to update the better value of m. I want to take a partial derivative of L with respect to c in order to take the better value of c, right? Now that better value might be up and might be down, right? Single partial derivative tells me, how much this particular parameter contributes in the betterment of loss, right? When I cumulatively put all of the partial derivatives in a vector, that is known as gradient. That tells me the direction and the magnitude where I have to go and how my loss function is going to be minimized, right? So a single partial derivative tells me the contribution of one single parameter, right, of that particular single parameter in, in improving the direction or in minimizing the loss. When I take, let's say, when I put m1, m2, m3, m4, m5, m6 and c all in one column vector, that is known as my gradient vector, or that is nothing but my gradient. Now at the core, this is simple gradient descent. Just take the partial derivative with respect to all the parameters and keep on updating the parameters, right? Now let's get a little more nuanced. In case of a large language model, we might have 100 billion parameters, right? So does that mean I take the partial derivative of the loss function for with respect to all 100 billion parameters? Yes. So each particular single partial derivative tells you, for one single parameter, tells you the direction and the sensitivity in which, the loss is going to be minimized. When you stack all the partial derivative, let's say p1, p2, p3, p4, so on, p100 billion, and when you stack them in a column vector, now this has become the gradient of the model, right? Now this particular vector represents the direction in parameter space that can increase the loss the fastest, right? That can increase the loss. And therefore what we can do is we can move in the negative of this direction because we want to decrease the loss the fastest, right? In the update rule, we can use a minus sign and move the negative in the direction, right? So let's represent all of the parameters as theta. One single parameter is represented as p1. When I stack p1, p2, p3, p4, and so all p100 billion, and I can stack them in a column vector, I can call it theta, right? So theta, the column vector which contains all the partial derivatives, is known as the gradient of the model. Now it's not for one single parameter. Now it's the gradient of the model. Moving in the negative of this direction will decrease the loss the fastest. What is the gradient telling us? The gradient is the direction in parameter space, that has the potential to increase the loss the fastest. That's why we move in the negative direction, right? Because we want to decrease the loss. We don't want to maximize the loss. We want to minimize the loss, right? That is how, and that is why gradient descent works. Now, there is one more nuance. The nuance is, we know that feed forward pass, if the model is stacked from left to right, horizontally, let's say this is my token embeddings, this is my multi-head attention block, this is my layer normalization and add residual. Now this is my feed forward neural network block. Now this is my output head, right? Let's say this is my decoder only transformer, right? So feed forward pass is going left, right? Now backward pass or back propagation or gradient descent is going right to left, right? So the first parameter that is going to be updated is from the feed forward neural network. Then we will update, the layer normalization parameters, which is the scaling and shifting vectors. Then we'll come here. Then we'll update the output projection matrix, which is WO. Then we will update the WK, WQ, and WB, right? Then we will update the token embeddings, right? So what I'm trying to signal is we are coming right to left, right? Step by step, step by step. At the right, we first discovered the feed forward neural network, right? And at the leftmost, we will first discover the token embedding. So we are going in the opposite direction, right? So we are back propagating, we are updating parameters in this particular sequence, right? So what happens when the loss function has multiple nested variables and nested parameters? Then calculus helps you with something which is known as chain rule, right? Chain rule helps you unravel or, unroll the dependency of the variables and, gives you a directed acyclic graph of all the variables so that you can use that particular topology of the graph to differentiate, right? Chain rule is pretty simple. We can make a video on chain rule if that's needed. But what happens when the equation gets complex, when, let's say, parameter, we have nested equations and nested parameters, then chain rule basically helps you in differentiating, with respect to all the parameters. So chain rule is one particular mathematical framework that helps you in differentiating the loss function with respect to all the parameters, right? If the differentiation is not super straightforward, if it has nested variables, it will show you how you can unravel the topology in a directed acyclic tree or directed acyclic graph so that you can differentiate one by one, right? So if I want to summarize gradient descent is nothing but I would just say two lines. Take the partial derivative of the loss function with respect to all the parameters. Stack them in a column vector. This is your gradient, right? Now this is your gradient of the model, right? Now you update all of these parameters as, which is known as the update rule. So partial derivative and update rule. These two are the steps of gradient descent. Gradient descent is applicable for any complexity of neural network, whether it is a decoder-only transformer, encoder-only transformer, simple linear regression, logistic regression, shallow neural network, deep neural network, convolution neural network, anything, right? So right to left is back propagation, left to right is feed forward pass, right? So we are computing gradients for all the parameters, and then we are updating them or applying them simultaneously, right? So you have to just remember the crux and the intuition. So we talked about the mathematical intuition, and the conceptual intuition simply is that training is learning. Backpropagation is teaching the model. It is learning the model. It's not memorizing. It is learning the representation. It is minimizing the cost function, right? So I hope you remember all of these mental models and the frameworks that we talked about, and it helps you in reading more and more about backpropagation and in understanding, bookish definition of backpropagation and also intuitive definitions of backpropagation. Okay, cheers. I'll see you in the next video.